Oh, okay. Welcome everyone to today's lecture. So we're going to start by just recalling our main item from yesterday, which is the fundamental theorem of calculus. And here's a picture outlining the statement of it. So the setup basically is that we've got some function whose graph we're interested in. It's called f. So here's the graph of y graphed against t, which is the variable on the horizontal axis. And we're interested in the function a, which we referred to as the area accumulation function yesterday. So a here is the name that we gave it was the area accumulation function. And when you're studying this theorem, it's really kind of important to give yourself a few minutes to give some clear attention to what the meaning of this function a is and what it does. So one key point about it is that the variable with respect to which a is written is called x, and the dependence of a on x is via the upper limit here in the integration. That's okay. So for most of us, probably reading this integration notation is kind of new, but a habit to get into if we can is to read this by saying, well, what a of x does is it counts or it measures the area under the graph of the function f, which is written over here, between some left-hand endpoint r and the x, which is the argument of the function. So basically, a is a function of the variable x. What it does is it measures the area under the graph of f from some fixed r over as far as x. So this area that's colored in this pink color here in the picture. So a of x is that area shaded in pink. And so for a given function f, of course, the question of whether we can actually calculate the values of a is definitely open to a question. It will completely depend on what f is, whether we can or not. But in principle, we can understand what a does. It measures area under this graph from a left-hand endpoint r, which is fixed. It's sort of built into the definition of a to some x, which is allowed to vary, and the value of a obviously changes as we move x up and down. So think about x here as something that can sort of slide up and down the horizontal axis, and that area, that pink area, changes as we do. Okay, so the fundamental theorem of calculus doesn't directly tell us how to compute values of this a, but it tells us that the derivative of a at any given value x is just the value of the function f whose graph is written at that point. Okay, and in principle, what we have in mind here is the setup that we would know what this function f is, that we'd have a formula defining it in terms of t, and that we'd be able to evaluate it at particular points x. So the fundamental theorem of calculus tells us basically is, in that situation, we don't really know the values of a, but we know the values of its derivative. Its derivative is just this function f. Okay, and that's kind of going to be the key to being able to evaluate these areas. And also it's the kind of link between this problem of calculating areas under curves that we started with and the whole world of the theory of differential calculus that you already know quite a lot about from your work in semester 1. Okay, so that's the fundamental theorem of calculus. And I suppose it's, I think for me at least, when I learned it first, I think it's a remarkable thing that this area problem is connected to differential calculus via this theorem. It's a very powerful and sort of beautiful fact of calculus. That's one remark. And the second one is just that, I think it does take a little bit of getting used to, because, when you sort of try to understand this theorem, okay, there are of course tasks that you could do with it, and there are some of the current homework and some that we discussed yesterday, but kind of a lot of it is just sort of unraveling it for yourself and figuring out what's it actually saying. So I think it's something that kind of benefits from looking at it, going away again, doing something else, coming back and looking at it again, and sort of building up an understanding of it quite kind of gradually. So, okay, that's the fundamental theorem. Here's a little Zoom poll, just so that we can all do something. So this is the only one that we have for today. So let me just launch this question and you think about it for a minute, and then we'll just do it together and move on to talk about some other things. So hopefully you can see that question there. Question is, for a positive real number x, we define a of x, which is supposed to correspond to this area accumulation function, to be the integral from 0 to x of t squared minus 4. And the question is, what is a dash of 3? So what's the derivative of a at the value 3? So if you have a view about that, vote for one of these 4 options. I think you can only vote for one of them if I set up the question the way I intended. So I'll leave it open for a minute or so. Okay, I'm going to leave it open for another 10 seconds or so. About 80% of us have voted, or almost. So if 50 more people want to vote, great, but don't feel any compulsion. Okay, I'll leave it open for 5 more seconds. 3, 2, 1. Okay, there, so we'll stop it there. Okay, great. So thanks for participating, everybody, in that. So here's the result of our poll. We can't really decide these questions, of course, by popular vote, but anyway, we can note what the vote is. So the overwhelmingly popular answer there was the third one, which is 5, which was voted for by about 2/3 of us, and all the other options got some votes as well. So anyway, 5 was our most popular option. So let's have a look. So our question there is, so this is just an example of exactly this type of situation. So here in this problem, a of x is the integral from 0 to x of t squared minus 4. So I'm going to stop sharing the results and have a look at this this problem. And the question was, what is so the picture here, of course, and I suppose one thing about these problems is you can draw a kind of fairly representative version of the picture if you want to, but there's really you really don't have to. You can sort of tackle these problems purely on the basis of how they're written without engaging particularly with what the picture looks like. But if anybody likes the picture here, the graph that we're looking at would be t squared minus 4 passes through the point 0 minus 4. Of course, that graph, it passes through the point when t is 2, this t squared minus 4 is 0, so 2 is here. This graph is a parabola, which looks more or less like that. It passes through, its value is at 0 is minus 4, its value at 2 is 0, and it increases away from that. And so the function a, what it counts is area to the right of 0, so the left-hand endpoint of the picture is 0, and up as far as x. So if x is 3, for example, which is what we care about in this example, so 3 is here. And so the value of the function a itself at 3 would be the area accumulated between the graph of this function and the x-axis between 0 and 3, except that the part below the x-axis is negative. So the value of a at 3 would be sort of that yellow area, bearing in mind that part of it would be counted negatively. But that's not what we're asked for. We're asked for the derivative of a at 3. And the fundamental theorem of calculus tells us that the derivative of this area accumulation function, the instantaneous rate of change at a given point, is just basically the height of the graph at that point. So it's just the value of f itself at 3. So the fundamental theorem of calculus tells us that a dash of 3 is just the height of the graph of t squared minus 4 above the x-axis at time, or the t-axis at time 3. So it's just 3 squared minus 4, which of course would be 5. So it was option number 3 there, which was the one that was our most popular vote. So the coordinates of this point basically are 3 and a dash at 3. Just the y coordinate of that point where that point on the graph at 3 is actually the value of the derivative of this area accumulation function at 3. So I think for me at least, the way I've been able to understand this theorem is by really kind of thinking about this area accumulation function and what it is that it does. It gathers up all this area and it keeps track of it. And once you sort of have a clear picture of that, you can think about how that changes instantaneously as the right-hand endpoint of the region is changing, which is the x that we're looking at. Okay, so this is increasing with x if the graph is sitting above the x-axis. It's stationary at a point if the graph has 0 value there. You're not accumulating any area instantaneously. It's negative if the value of the graph is below the x-axis. So yeah, I mean, I think the thing that can make these questions a bit tricky is that there's so much information around, and you have to kind of identify what exactly is it that you're asked for. What's the function whose derivative you're looking at? Is it the area accumulation function, or is it the f, or is it something else? And figure out exactly how you can apply the fundamental theorem. So maybe what I'll do actually, there's a couple of questions like this, as you know, in the current homework, and I might just post a little video with a few more examples just to give us a bit more, a few more to go on, if that would be of any use. But I'll do that in the next couple of days. Okay, anybody have a question about any of that? Okay, great. So if you do, just shout or put a question into the chat at any stage, and I'll keep an eye out. Try to notice if the questions appear there. Okay, so that's where we're at this point. And okay, we're going to kind of move on a little bit now to more practical concerns, as I said. And the fundamental theorem will still be our key theoretical tool, but we won't be referring to it as much. And also, we're not going to formally prove it, but if you want to look at a proof, you'll certainly find one in Stewart's book or other calculus textbooks, and you'll find some more discussion about it also in the lecture notes. But I think it is useful to think about how this area accumulation function is changing when x moves around, and you can kind of get a feeling there for what this theorem is really saying. Okay, so I would claim that the fundamental theorem is interesting because it connects differential calculus to the problem of calculating areas under curves. And in the same regard, really, it's useful because we know a lot about differential calculus. We've got a lot of theory there. We know how to calculate derivatives. We've got basically a sort of collection of rules for doing that: the chain rule, the product rule, etc. And so, given this connection, all that knowledge should be useful in calculating integrals as well. And then just a historical remark: the fundamental theorem of calculus it goes back really to the middle of the 17th century and to work of Newton and Barrow, who was less famous than Newton, but also was an important contributor to the development of calculus. Okay, right, let's finally see how do we actually use this fundamental theorem to calculate some definite integrals. Okay, so this example, we're going to calculate the definite integral from 1 to 3 of the expression t cubed minus t squared. Okay, so a couple of remarks about this. First of all, I don't know, I mean, we're going to do a lot of these examples, and you sort of get into a frame of mind where you're just sort of doing them and practicing them all the time. And, of course, you can pick up a calculus textbook and check the answers and so on and kind of get very good at doing these examples. And we're going to have a way of doing them that becomes kind of somewhat kind of mechanical in our minds, I think. But I think we should also not lose sight of the fact that it is sort of a remarkable thing that in the space of a few minutes, we're actually able to compute areas like this. The region that's bounded by the graph of t cubed minus t squared, above and left and right by 1 and 3, below by the horizontal axis, that's a pretty complicated region. So I think, to me, it's still amazing when I think about it, that we actually can compute areas of regions like this relatively easily and without too much trouble. So, okay, so a quick picture. Our problem is to calculate the area from 1 to 3 of t cubed minus t squared. When t is 1, t cubed minus t squared is 0, so the graph sort of passes through the point 1, 0. When t is 3, t cubed is 27 and t squared is 9, so t cubed minus t squared is 18. And so t cubed sort of grows faster than t squared when x is greater than 1 or when t is greater than 1. So the graph is something like this. I mean, I'm not saying that this is an accurate picture, but this is the point. Whose coordinates are 3 and 27 minus 9 is 18. This is the point whose coordinates are 1, 0. We don't really care, but when t is 2, then t cubed is 8 and t squared is 4, so this is the point 2, 4. So this function is growing, and we're looking at an area like this. Okay, its upper boundary is the graph of that cubic polynomial, t cubed minus t squared. The pink line there is the line y equals t cubed minus t squared. Okay, and so I'm going to sort of try to, for this example, try to explain it in terms of the fundamental theorem so that we can see how we're applying the fundamental theorem. But in reality, we're not going to do all this fussing every time. We're just going to sort of apply the method without dwelling on the theoretical justification for it. So this sort of long-winded approach is only for this example, just so hopefully we can see how we're justifying the technique that we're going to use. That graph is not supposed to look like a straight line. But to be part of the nice thing about this is that we don't actually need to know what it looks like in order to answer the question. Okay, so to tackle this with the fundamental theorem, we're going to imagine that we have some point R, which appears in the fundamental theorem statement, and that R is somewhere way off to the left. Okay, we don't care where it is as long as it doesn't really sort of interfere with the part of the picture that we're interested in. It's somewhere off to the left. And we're going to define the area accumulation function A to be the integral from R to X of t cubed minus t squared. So the graph, of course, continues, to the left of 1. I've only drawn the part of it that appears in the region that we care about. T cubed would be negative, of course, when t is negative, so the graph can drop below the x-axis. Okay, so a of x is the integral from r to x of t cubed minus t squared. Okay, and then the assertion is that if we knew how to evaluate a at different points, then the integral from 3 to 1, or from 1 to 3 of t cubed minus t squared would be the value of a at 3 minus its value at 1. Okay, so we'll draw a bit more of the graph here. So maybe it goes like this somehow. Okay, so a of x is the area to the right of r as far as x. So a of r, a of 3 is all the area accumulated between this graph and the axis from r all the way up to 3. A of 1 is all the area accumulated between this graph and the horizontal axis from r as far as 1. So 1 is here. So if we want to know the area that's kind of enclosed between 1 and 3, which is this pink bit, then that should be everything, all the area to the left of 3 minus all the area to the left of 1. So basically, when you're looking at this expression, I'm sort of wondering, where does this come from? Where it's saying that a of 3 includes all the area from 3 to the left until you hit this r, wherever r is. And a of 1 includes all the area to the left of 1 as far as r. So if we want to know the area just between 3 and 1, well, we want everything that's to the left of 3, but not to the left of 1. So we should subtract off the stuff to the left of 1 from the stuff to the left of 3. So that's the justification for this assertion, that what we want is the value of a at 3 minus the value of a at 1. So I guess it's explained probably more clearly in this last line. What we're talking about is the area under the graph that's to the left of 3, but to the right of 1. Okay, so it should be that difference. Okay, that's fine, but like, great. We don't know how to compute a of 3 or a of 1, so how are we going to do this? Well, what we do know about a is its derivative. Okay, so if we had a formula for a of x in terms of x, we could use it to evaluate a of 3 and a of 1, and that would be it, we'd be done. Okay, so what we know about the function a of x from the fundamental theorem is that its derivative at a point x is just what we would get by plugging x instead of t into t cubed minus t squared. So it's just the height of the graph of f above the x-axis at the point x. So we know that a dash of x is x cubed minus x squared. Okay, the derivative of a is x cubed minus x squared, and that's the part where we're really applying the fundamental theorem. Okay, then we have to ask ourselves, well, what sort of function has derivative x cubed minus x squared? And here we have to reverse our differentiation process to come up with an answer to that. Okay, and so we're going to, really our business for the next week or two is going to be to develop techniques for answering this question. How do you find a function that has a given derivative? Okay, and a lot of it is kind of a little bit ad hoc. It's not like differentiation where you have rules to apply. You say, okay, you have to identify, do I want the chain rule here or the product rule, or what do I need to do? This is kind of a little bit more experimental and a little bit more ad hoc and a little bit more kind of trying to use your ingenuity to figure out what might work. But we are going to have a certain amount of kind of recipes that will help us in many situations. Okay, so what would have derivative x cubed minus x squared? That's what we have to ask ourselves. Okay, well, let's start with the x cubed part. Now, what do we have to differentiate to get x cubed? Well, we have to kind of differentiate a fourth power to get a third power. And this is an attempt at sort of kind of explaining the thought process that a person might enter into when answering a question like this. The text of it is not really what I'd expected to write. It's supposed to kind of be a description of how we would think about it. So, the question we're asking ourselves here is, what do I have to differentiate to get x cubed? And maybe, at least for me, the first approximation to that is, well, x to the fourth. Differentiate a fourth power, you get a third power. But if you differentiate x to the fourth, you don't get x cubed, you get 4x cubed. So you get something that's wrong by a factor of 4. So you have to compensate for that by multiplying by a quarter. Okay, but if you differentiate a quarter x to the fourth, you get a quarter times 4x cubed, which is x cubed. Okay, so that answers part of it. What we need to differentiate to get x cubed is 1/4 x to the fourth. Okay, fine, that sort of answers the first bit. What do we have to differentiate to get minus x squared? Well, okay, same thing. What do you have to differentiate to get a square? Well, you have to differentiate a cube because the exponent drops by 1. You differentiate. So if I differentiate x cubed, I get 3x squared. That's not what I want. It's wrong by a factor of 3 and by a sign. I want to get minus x squared. So instead of x cubed, I should take minus x cubed because I want to get a negative x squared in the answer. But also, x cubed is too big by a factor of 3. It gives me 3x squared if I differentiate it. So I should compensate by that by dividing by 3. So if I differentiate minus 1/3 x cubed, then I get minus 1/3 times 3x squared. So I do get minus x squared. And then we know that the differentiation operator is linear. If I differentiate 1/4 x to the fourth minus 1/3 x cubed, I get x cubed minus x squared. So that's an answer to the question. Okay, so this is sort of deliberately sort of an ad hoc attempt to describe how we might think about this. We are going to formalize it a little bit. I mean, what we're basically saying is, if you want to get something whose derivative is x cubed, you need to increase the power by 1 to 4, but also you need to divide by 4 to compensate for the 4 that would appear in the derivative. So basically, to find an antiderivative for x cubed, something whose derivative is x cubed, I should increase the power by 1 and divide by the new power, so I get 1/4 x to the 4th. So we will have a few rules like that, but we'll have to be able to kind of apply them in an adaptable way. Okay, so the goal there was to find something whose derivative is x cubed minus x squared, which would be a candidate basically for the area accumulation function for our problem. Okay, and we've succeeded in doing that. We have found something whose derivative is x cubed minus x squared. So of course, you might be wondering, well, okay, fine, we've done this, but there are lots of things whose derivative is x cubed minus x squared. This is not the only one, and actually this example isn't what it was supposed to be. It's missing something here. If you take 1/4 x to the 4th minus 1/3 x cubed and add on your favorite constant, like 20, that's another example of something whose derivative is x cubed minus x squared. Because when we differentiate this thing, the derivative of the constant part is 0, it doesn't change the answer. So basically, if you have an answer to this question, what's something whose derivative is x cubed minus x squared, you can change that answer by any constant value at all. You can add or subtract any constant, and you'll have another answer to the question, which is equally good, which also has the same derivative. So we only need one answer. And basically what these different answers correspond to essentially is taking different, so remember what we're trying to calculate are candidates for this area accumulation function. We've got our function f, and we're talking about area accumulated under its graph from some left endpoint r to some x. It's the usual picture. So what different choices of this constant correspond to basically are just different choices for that r, that left-hand endpoint. And of course, that's, you know, that's kind of assumed to be fixed, but not specified. We're not giving it a particular value. So if we were to insist on a particular value, that value would determine some constant that would be included in this expression. But the point is, what we need to calculate is the value, is the integral from 0, no, it wasn't 0, it was 1, the integral from 1 to 3 of t cubed minus t squared. And for any of these alternative versions of the area accumulation function for different sort of left-hand endpoints, that value is always the value at 3 minus the value at 1. So it doesn't really matter. If constant c, if we were to include some constant there other than 0, it would just get cancelled in this subtraction anyway. So it wouldn't actually enter the answer. So we basically just need to take one example of an expression whose derivative is x cubed minus x squared. So we have one. And then the final step is just to evaluate that thing at 3 and at 1 and take the difference. So we take a of x to be this one. Its derivative is the thing that we want. 1/4 x to the 4th minus 1/3 x cubed. Evaluate that at 3 and you get 81 over 4 minus 27 over 3. Evaluate it at 1 and you get 1/4 minus a third. And hopefully, if I've done the calculation right, when you subtract the value at 1 from the value at 3, you get 34 over 3 as the answer. And so what that tells us, and again, I'm going to come back to this because I still think it's sort of remarkable, is that for this function, whose graph is t cubed minus t squared, the area of this funny shaped region that it encloses between 1 and 3 and the x-axis is 34 over 3. So it's that rational number. It's not even obvious in advance that it should be a rational number. Certainly not that its value should be 34 over 3. So what this is telling us, and this example is, I suppose, relatively easy because our function was just a polynomial function, is that generally speaking, if we can find functions whose derivative are the things defined in these graphs, then we can actually compute areas of all of these regions, which can be incredibly complicated, convoluted things. And, you know, relatively easily using this method, we can often find their areas, which I think is, you know, even though when you're practicing the examples, you know, generally you do sort of loads of them and the technique is basically the same for all of them. It can be very easy to sort of lose sight of what it is that you're doing in terms of these regions whose area is being calculated. But yeah, we can, it's remarkable how many things, how many areas of what sort of complicated regions we can actually compute precisely using differential calculus. So I suppose I'd remind you to sort of occasionally think about how striking that is when you're working on examples which generally involve computing numbers and, you know, confirming that you're applying the techniques correctly. Okay, anyone have a comment or a question about any of that? Okay, so we're going to do loads more examples like this essentially for the next little while, except that we're going to develop some techniques a little bit more than a little bit better than the stream of consciousness approach there to that example to figure out what these antiderivatives are. So here is another version of the fundamental theorem of calculus. I really don't expect you to dwell on this slide at all. I'm just putting it up here in case it appeals to anyone. It's kind of a formal statement of what we just did. So some people state the fundamental theorem in different ways. And so this theorem, if you like it in this formal form, sort of says what that technique is that we just applied. If you don't, and if you prefer to just kind of follow the steps in the example, that's absolutely fine. But in case anybody likes this version of the statement, it's kind of an instruction about how to use the fundamental theorem to calculate a definite integral. What it says basically is, if you want to calculate a definite integral from a to b of some function f, first of all, find a function capital F, whose derivative is the little f. Okay, that might be hard. And actually, that's going to be what we're going to occupy ourselves with now, techniques for trying to do that. But if you can do it, then to calculate the definite integral, what you need to do is just plug the values a and b, the limits of integration, into your capital F, subtract the value at a from the value at b, and that thing is your definite integral. And that's what we just did for that example. So, you know, if you prefer to kind of keep the technique from the example in your mind rather than referring to this theorem and interpreting it, that's absolutely fine. If you like to have the kind of compact statement there, that's fine too. So whatever you prefer. Okay, that was section 1.3. So it's an important section, I'd say. It's a, you know, it's sort of really sort of like I said before, the key conceptual ingredient of all of our work on integration. So after studying this section, what I hope you might be able to do would be kind of explain what's meant by an area accumulation function, state the fundamental theorem of calculus, the first version of it, I guess, is sort of the key version. Use it to solve problems similar to that one that we just talked about with t cubed minus t squared. Okay, describe the general strategy. Well, actually, to be honest, that's not a learning outcome from this section so much as something that we're going to be doing again and again in the next section. So you'll be able to do that all right. And evaluate some examples of definite integrals like the one in that last example. Okay, so hopefully that's a sort of reasonable target for study in this section. If it isn't, let me know, please. And if anything is not clear about what we're supposed to be doing. Okay, section 1.4 is the long one in this chapter, and it's going to be divided up into various subsections. So where are we? Yeah, we have a few minutes left. So really, this is techniques of integration. So I suppose what we've established in the last section is that if we want to be able to calculate definite integrals like this, for some specific version, example of f and some specific values of a and b, then what we need to be able to do is find a function whose derivative is this little f. And okay, that's not too bad if little f is x cubed minus x squared. But if little f is cosine of 3x times x squared or something, it's a bit harder. And we don't have, you know, we just don't have a toolkit like we have for differentiation that allows us to do this. So in this chapter or this section, what we're going to be doing is basically developing ways of trying to kind of do reverse versions of the rules of differentiation, the chain rule and the product rule, to enable us to tackle the problem of finding functions who have specified derivatives. Okay. We're not going to be much talking about the fundamental theorem of calculus very explicitly, but I think to keep your eye on the ball and to remind yourself of, you know, what the bigger picture is, it's useful to sort of have that in the back of your mind all the time. Otherwise, you can get sort of quite, at least in my experience, quite bogged down in endless examples. Okay, so that's basically a repeat of the second version of the fundamental theorem of calculus. So, but that's what we have to do to calculate a definite integral. Okay, so a couple of words about notation. There's a lot of notation around this, and I know some of it is not the most user-friendly in some ways when you first encounter it. So just a remark. This is a bit of shorthand that can be quite useful. If you have some function, capital F, and you need to evaluate it at certain points and subtract the value at one place from the value of another, then this notation is kind of introduced to just make that a bit more convenient and compact. And so basically, it's just basically what you do is you write a kind of a vertical slash to the right of your function and the values, the limits of integration above and below. So for example, if you wanted to say something like, let's say x squared, if you wrote something like this, x squared, and let's say you put a 3 here and a 2 here, like that. Okay, forget it, this applies even, the only place you ever see this is in integration, but you can interpret it anyway. What this shorthand notation means is that it's just what you would get if you plug 3 in for x minus what you would get if you plug 2 in for x, which would be 9 minus 4, which would be 5. Okay, so it's just a little bit of notation for making some of the calculations and the recordings of what we're doing convenient while we're writing the solutions to definite integration problems. So if you see that notation, just, it's handy to use, first of all, and you know what it means. Okay, so that's just a bit of shorthand. And then here's another bit of lingo, which you probably already met with Graham in semester 1, I think. But if you have some function little f, a function capital F is called an antiderivative of little f if the derivative of capital F is little f. So, for example, x squared is an antiderivative of 2x. That's just saying that the derivative of x squared is 2x. So it's a lot of words, but when you want to kind of emphasize that you're moving from 2x to x squared, rather than the other way around, you might refer to x squared as being an antiderivative of 2x, rather than referring to 2x as being the derivative of x squared. And of course, there's lots of other antiderivatives of 2x, but they all differ from x squared just by a constant, something whose derivative is 0. So generally, we talk about an antiderivative of a function rather than the antiderivative, because there's more than one of them, but they all resemble each other closely. They only differ from each other by a constant. So I suppose, yeah, the point of this slide is just there are two pieces of notation and language that are useful to have in our vocabulary. One is the term antiderivative, and the other one is this notational device for referring to the difference in the values of f at b and at a. Okay, so hopefully that's a useful reference if we encounter these terms again and again, and you want to remind yourself of what to say. Okay, another bit of theoretical or conceptual machinery. Okay, so our focus now is kind of moving to this problem of calculating or finding antiderivatives. And we talked about definite integrals, and I never gave a justification for why they're referred to as the definite integral, why we have this word definite flying around. And the reason is there's something other animal called the indefinite integral. So the indefinite integral of a function, which is written this way, and the difference between this and the definite integral is that there are no limits of integration on the integral sign. That's how it looks different. So, an example so far, we've had some numbers appearing there above and below the integration sign. They're missing here. That's how we know it's an indefinite integral rather than a definite integral, which is kind of a subtlety built into the notation. But what this is it's the so-called general antiderivative of the little function f. So, for example, if we were to take the indefinite integral of 2x, so it's written the same way as a definite integral, except that the limits of integration are missing. What that means is an expression in x whose derivative is 2x. We've already noted that x squared is such a thing, but sort of the collection of all such expressions. So x squared plus any constant. So basically, this is sort of a collection of expressions, because the constant can be any real number, but it's a set of all things whose derivative is 2x. So basically, anything whose derivative is 2x is x squared plus c for some c. This expression is referred to as the indefinite integral of f. It's the general antiderivative of f. And so again, I think the notation that surrounds this whole subject of integration is probably not what we would invent if we were inventing it now, but it sort of evolves this way. Notationally, the difference between the definite and an indefinite integral is just that the limits of integration don't appear in the indefinite integral. But in terms of what they mean, they're totally different things. Related, but very different. The indefinite integral of 2x is this expression x squared plus c. It's the collection of all things whose derivative is 2x. So it's basically like a collection of functions that differ from each other by a constant. Whereas the definite integral of 2x over some interval is a number. It's the area of some region. So, the indefinite integral will always look something like this. And the definite integral over any region is just a value. It's a number. So, for example, if we were to integrate from 0 to 1, 2x dx, that would be x squared evaluated at 1 minus x squared evaluated at 0. So it would be 1. It would be a number. So, these two things don't resemble each other at all. But when you write them in integral form, they resemble each other very closely. Okay, so but anyway, in any case, I suppose it's certainly having the concept of the indefinite integral at our disposal is a useful thing, because what we care most about now is being able to find antiderivatives. And so this indefinite integral is a kind of, I suppose, a notational and vocabulary device for that. Okay, so indefinite integrals are basically antiderivatives. Definite integrals are basically areas of regions. Okay, so here are a few examples. So we'll maybe have a look at one or two examples, and then we leave it for this week. So supposing you had the problem of determining the indefinite integral of cosine of 2x. Okay, so there again, we're asking ourselves, what do I need to differentiate to get cosine of 2x? Okay, so, and you have to kind of put yourself back in the world of studying differential calculus, but kind of trying to reverse the rules. So, okay, we know about derivatives of trigonometric functions. And if we can answer this question, of course, it means that we can calculate areas under the graph of cosine of 2x over specific regions. So what do we need to differentiate to get cosine of 2x? Well, okay, so again, ask ourselves, what do we need to differentiate to get cosine? And the answer to that is generally sort of sine, because when you differentiate sine of x, you get cosine of x. Okay, derivative of sine x is cosine x, fine. So we don't want cosine x, we want cosine of 2x. So what would I have to differentiate to get cosine of 2x? Well, something like sine of 2x maybe. Okay, so this is kind of a sort of step-by-step, kind of iterative sort of experimental strategy mentally. I don't expect you to sort of document all these improving guesses, but we're kind of trying to get at something whose derivative might be cosine of 2x. Okay, so suggest maybe differentiate sine of 2x, the answer should be something like what we want. But if we differentiate sine of 2x, we have to apply the chain rule, and that says that we differentiate sine of 2x, we get cosine of 2x times the derivative of 2x, which will be 2 times cosine 2x. Okay, so if we differentiate sine of 2x, we get almost what we want, but we get twice what we want. Okay, but fortunately, handling sort of constant multiples in the differentiation operator is not too bad. If differentiating sine of 2x gives us twice what we want, then we should differentiate half of sine of 2x to get exactly what we want. Okay, so basically this factor of 2 that appears, we have to sort of compensate for that by differentiating half of sine of 2x instead of sine of 2x itself. So if we differentiate half of sine of 2x, the half we can pull out because it's a constant factor. We get cosine of 2x times 2 by applying the chain rule. The 2 cancels the half, and we get cosine of 2x, which is what we want. Okay, so what we're saying there is that 1/2 of sine of 2x is a function whose derivative is cosine of 2x. So it's an antiderivative for cosine of 2x. Every other antiderivative of cosine of 2x differs from this one by a constant. So the indefinite integral of cosine of 2x is somehow the collection of all functions whose derivative is cosine of 2x, and that's basically things of the form 1/2 sine of 2x plus c. So the c is referred to usually as a constant of integration. It turns out when you take a general antiderivative, it's not so important generally, and you kind of get into the habit of just sort of carrying it around all the time and writing plus c, kind of also almost as a little sort of automatic addendum to everything. But it's important in applications. In particular, it's important in things like differential equations, where people are modeling, for example, physical situations with differential equations, and maybe you're modeling like the heat flow in a plate or the fluid flow in a pipe or something like that. And you have some initial conditions or some boundary conditions where you know what's happening at the start of the setup, or you know what's happening on the boundary. And actually quite often when you solve some differential equation and you get some statement that involves a constant of integration, and the value of that constant of integration can be determined by the physical situation in the initial conditions or in the boundary conditions. So if anyone's interested in modeling with differential equations in applied maths, you'll sort of see quite often how the constant of integration plays a role there. For our purposes right now, we just have to bear in mind that it's there when we take a general antiderivative. It includes this constant of integration. Okay, so that was an attempt at sort of trying to describe again the thought processes that we might go through if we're trying to answer a question like this. I suppose what I'd suggest maybe you think about this week, if you have a chance, just kind of making sense of that for yourself, and see if you agree that this is how somebody might approach this problem, or have an alternative approach yourself. We are going to kind of formalize this a little bit more by kind of formalizing some sorts of techniques of integration that apply some of the time, but it is a bit more ad hoc than the rules of differentiation, which can be applied in a fairly uniform way. So next week, really, this section is called Techniques of Integration. And what we're going to do, it's going to take us more than next week. It's going to take us at least the next 3 or 4 Wednesday and Thursday meetings, is to just kind of develop some slightly more formalized versions of these techniques of integration that don't rely quite so much on sort of, well, what kind of thing would be a reasonable guess and how do we adapt our reasonable guess? We'll make it a little bit more systematic than that, but we'll still be relying on guessing quite a bit, as we'll see. Okay, so we'll leave it there for today with that example. I'm going to stop the recording now and thank everybody who's joined us for the recording, and we'll see you next week, everybody.